Hey everyone. So this topic is about cardiac physiology, and I'm going to start with the basics first, okay? Because again, you have to know your foundation and your basics before you go on to even think about pathology or pathophysiology, okay? All right. So the first thing, again, this is cardiac. So let's just draw a quick picture of the heart, okay? And I'm just going to draw it like this for now, just so that we can just learn better this way, okay? So we can draw it. Now, so we have our right atrium, right ventricle, left atrium, left ventricle, right? Okay, now let's go over some anatomy. What drains into the right atrium? We have our inferior vena cava here, right? Which brings blood from all of our lower extremities up here, okay? Now, what drains blood up top here, brings blood to the right atrium, is the SVC, superior vena cava, which brings blood from the subclavian veins, all from our upper extremities, right? It all comes here into the right atrium. Blood from here will go into the right ventricle. From the right ventricle, well, where will it go? It'll go to the pulmonary artery, right? Once it goes to the pulmonary artery, where does it go? The lungs, right? Okay. It'll go to the lungs. From the lungs, it gets oxygenated, and I'll go over this more in detail in another lecture. Goes back to the left atrium, right? Through the pulmonary veins. Okay? From the left atrium, the blood is now oxygenated, goes into the left ventricle, from the left ventricle into the aorta, right? Okay. All right. Okay. So now let's talk quick thing about end-diastolic volume. What's end-diastolic volume? Exactly what it says. Diastole is when the heart is filling and relaxing, filling with blood, right? This is the volume of blood in the left ventricle at the end of diastole. Okay? So when the heart has completely filled with blood and is relaxed and is about to contract and send it out, that is my end diastolic volume, the amount of blood in my left ventricle at the end of diastole. Okay, this is the same thing as preload. Okay, preload. That's exactly what preload is. It's the amount of blood in my left ventricle. Okay, that's about to be sent out into the aorta. All right. Now, preload, yeah, it's the same thing in the right ventricle. There's preload in the right ventricle also. But for the test and most of the USMLE questions, whenever they talk about preload and end-diastolic volume, most of the time they're always talking about the left ventricle. Okay? Now, there's a certain amount of blood that's in the ventricle here at the end of diastole, right? Let's say 10 cc's. Now, I'm going to redraw this just to give you guys a better idea, okay? Okay. Alright, now let's redraw this. I'm going to draw it more of like a box, okay? Okay. Now, we talked about the end-diastolic volume, the amount of blood that's here, right? So let's talk about now the end-systolic volume. What's that? It's the amount of blood left in the ventricle after the heart is contracted, okay? Volume of blood in the left ventricle at end of systole, right? So what happened? My ventricle filled with blood, it contracted, sent out some blood, and whatever blood is left over is my end-systolic volume. Now, the thing here, I think, a lot of students learning physiology for the first time, the amount of volume or blood that's in the left ventricle, not all of it will be sent out into the aorta, okay? All right. So let's say for theoretical purposes, if I had an end-diastolic volume of 10 cc's, okay, of blood in my left ventricle, do you think all 10 cc's would leave the left ventricle and 0 would be left over? No. The real heart, the way the real cardiac physiology works is that if I had 10 cc's in the left ventricle, some would be left over, okay? You don't have to know how much exactly, but you should just know that some is always left over, okay? And the amount that's left over is my end systolic volume. So let's say 10 cc's is my end diastolic volume, right? And I send out 5 cc's into the aorta. What's my end systolic volume? Well, if I had 10 to begin with, 5 went into the aorta, what am I left with? 5 cc's. That's my end systolic volume. Makes sense? Okay? So we know these. Now, the difference between these two is my stroke volume. Okay? The amount of blood that actually went into the aorta when the ventricle contracted is the stroke volume. Okay? The amount of blood that actually leaves the ventricle. Okay? Stroke volume. And again, the difference, my end diastolic volume minus my end systolic volume, will give me my stroke volume. Okay? So the lower my end systolic volume, what would happen to the stroke volume? If my end systolic volume is low, that means my stroke volume is probably high, right? How does that make sense? Because if I had 10 cc's to begin with, and let's say I put out more now, let's say my end systolic volume was only 2 cc's. Well, that means that 8 cc's went into the aorta. Make sense? Okay? Very simple formula. Easy to remember, but really, really good concepts, okay? Really important to know and understand these concepts well, okay? So now, let's talk about the next concept called ejection fraction, okay? Always known as EF. Now, you'll see this all the time in the hospital on a bunch of questions on the USMLE, and this is why, what's so important about congestive heart failure. But before knowing that, you have to know what ejection fraction is. This is the stroke volume over the end-diastolic volume. Okay, now you're thinking, well, what does that mean? Okay, that means that there was a certain amount of blood, 10 cc's, right, which is our end-diastolic volume, right, that we had in the beginning. We had 10 cc's in the ventricle. That was our end diastolic volume, our preload. Okay, how much we began with. But there's a certain amount that we contracted out. What was that amount that we contracted out? 5 cc's, right? What do we call that? The stroke volume. The stroke volume is how much we send out. So 5 cc's was our stroke volume, right? What the ejection fraction is a ratio. It says, okay, well, how much blood did we have in the beginning and how much blood did we send out? It's a fraction. It's 5 cc's out of the 10 cc's, okay? So it would be 1/2 or more like 50%, okay? Now, in in normal healthy patients, normal ejection fraction is about that much. It'll be about, it could be 50%, 55, 45%, somewhere around there, okay? But all that's saying is that it's sending out half of whatever it had in the beginning. If it had 10 cc's in the beginning, it sent out half. If it had 20 cc's, it sent out 10. Make sense? Okay, so it's really important to know this. Now, let's look at this a little closer now. Whenever you have a formula here, you can look at it in two ways. The first way is actually look at it physiologically and think about it in physiology terms, but then mathematically also. This is the numerator, right? And the denominator. Okay? Now, if I increase my stroke volume, my numerator, what would happen to my ejection fraction? It would also increase, right? That makes sense, right? Because if I had, let's say, first I had 5 cc's as my stroke volume and 10 cc's as my end diastolic volume, what if I change that now? Now I increased my stroke volume to 8 cc's, but I left my end-diastolic volume the same. What happened to my ejection fraction? It's 8/10 now, okay? It increased. Why? It's because I increased my stroke volume. Make sense? Now, let's leave my stroke volume the same. Let's leave it 5 cc's. But let's increase my end-diastolic volume to 20. Okay. My stroke volume is the same. I just increased my end-diastolic volume, my preload. So that means, what does that mean? That means that I'm only sending out a fourth of what my ventricle had in it. My ventricle had 20 cc's of blood in it, but I only sent out 5 cc's, and that's 25%, which is my EF. Okay? Okay? That is something more along the lines of congestive heart failure. Okay? Why did that change? What happened? My preload increased, but my stroke volume didn't. Okay? Now, this is getting back to a very simple physiology concept that you learned early on, is that as preload increases, stroke volume increases. Let's go over that. Okay, this gets to the Starling Curve now, okay? And I know you've probably seen this before, but if you're having a tough time understanding it, let's go over it, okay? What's on the x-axis here? Preload. What's on the y-axis? Cardiac output or stroke volume. They're almost the same thing. If I increase my stroke volume, I increase my cardiac output. If my cardiac output's increased, most likely the stroke volume's increased, okay? The first thing you do whenever you see a graph, and I'm telling you, you'll see a lot of graphs on step 1, is you look at the axis. Look at what the x-axis is, look at the y-axis. Preload and cardiac output, okay? And stroke volume. What do I see here? What happens? As preload increases, stroke volume and cardiac output increase. Okay, that's how you should be reading this graph. You should say to yourself, well, as preload is increasing, what's happening to my stroke volume, cardiac output? It's increasing also. That makes sense, right? Because let's look at a heart. Okay. Okay, if I'm increasing the amount of blood that's in my ventricle here, what's going to happen to the amount of blood that actually leaves? It'll also increase, right? Why? Is because of the stretching forces on the ventricle. Okay, there's a law that actually says that as the myocardium actually stretches outward because of more volume of blood, as it fills more, as it has more preload, what does it want to do? It contracts back even stronger. Okay? The more it stretches, it says to itself, hey, there's a lot of blood in here, I need to get it out. So the more preload that's in there, that increases the contractility. And by doing that, it increases stroke volume. What's contractility? It's the force with which the ventricle contracts with. If it's contracting with a stronger force, it's going to send out a lot more blood, okay? What is that going to do to my stroke volume? Increase my stroke volume. If I increase my stroke volume, what will that do to my cardiac output? Increase my cardiac output. How do I know that? Because the cardiac output is stroke volume times heart rate, right? If I'm increasing my stroke volume, what am I doing to cardiac output? Increasing it, right? Makes sense? If I decrease my stroke volume, I decrease cardiac output, okay? So this is exactly what this graph is showing us, is that as preload increases, as the amount of blood filling this ventricle increases, the amount I send out increases also, okay? So my ejection fraction, would probably be good here, be a good amount.